Chapter 2, Part 4, Properties of Organic Compounds. First, let's talk about the physical properties of organic compounds. Physical properties include boiling point, melting point, and the physical state or phase, and the solubility. These properties are dependent on the molecular weight and the structure of the compound, as well as the intermolecular forces between different molecules of the compound. So let's start by reviewing intermolecular forces. Intermolecular forces are the interactions between molecules. These depend on electrostatic attraction. So our main IMFs that we're going to consider are ion-ion forces and van der Waals forces, which includes London dispersion forces and dipole-dipole forces, and then also hydrogen bonding. So let's talk about ion-dipole forces. These are forces that exist between an ion and the partial charge on an atom in a polar molecule. So let's say we take sodium chloride and we put it into water. We know that sodium chloride dissolves in water, but what is actually happening in that solution? We have the sodium plus ion, which has been solubilized by water, and now water has organized itself around the sodium plus ion. So remember that water is polar, and so we're going to have these dipoles along the water molecules, which means that there is a partial negative charge on each of these oxygens and a partial positive on the hydrogens. That's not as important for this particular interaction. This means that the partial negative charges are going to be attracted to the sodium plus ion, and depicted in this very light blue are those interactions. Let's circle them just in case you didn't notice them appearing. Now, the chloride has also been solubilized, and it is also being surrounded by water molecules, being solvated. And this is where that partial positive on the hydrogen becomes important, because the partial negative of the oxygen is away from the chlorine because it is electron dense. So those electrons are going to be repelled. But these hydrogens are partially positive, and they are going to be attracted to the negative charge of the chloride ion. So these are ion dipole forces. The ions have a full charge, and the water molecules just have a dipole that has caused partial charges. Next, we're going to discuss dipole-dipole forces. And these exist between the partial charges on atoms in two polar molecules. And these can be two molecules of the same compound or two molecules of different compounds. So, for example, if we have chloromethane, two molecules of chloromethane are going to have an attraction between each other because this molecule is polar. There's going to be a dipole towards the chlorine, which means that the chlorine is partially negative, the carbon is partially positive, and so is the hydrogen. The electron density of the molecule is flowing towards the chlorine. So the partial negative on the chlorine and the partial positive on the hydrogen are going to interact. You see the same thing in acetone. Acetone is a polar molecule as well. You're going to see partial negatives on the oxygen and partial positives on the carbonyl carbon. And you'll see interactions between those as well. So let's talk about hydrogen bonding. Hydrogen bonding is a very strong dipole-dipole interaction, which only occurs between hydrogen atoms that are attached to highly electronegative atoms, such as oxygen, nitrogen, or fluorine, and non-bonding electrons on another. Hydrogen bonding is really important even within our own bodies. There are hydrogen bonds between atoms within our proteins. That's what causes protein folding, and even holds together our DNA. So hydrogen bonding is really prevalent in water as well. So again, we know that water is polar, partial negative on oxygen, partial positive on hydrogen. So in water, you see an interaction between hydrogen of one water molecule and oxygen of another. So this is the prevalent force that holds water molecules together and gives it such a high boiling point. You also see the same thing in alcohols. So below you see molecules of ethanol pictured. They have the same partial negative, partial positive, partial negative, partial positive, same type of hydrogen bonding as water, which is one of the things that makes alcohols so similar to water. And then you can also see the same thing in amines. That bond between the hydrogen and the nitrogen is going to be polarized, so that you have partial negatives on the nitrogens, partial positives on the hydrogens. Now, London dispersion forces are possibly the most complex force to understand, and they're also the weakest of all the forces. They have kind of a misnomer. It says dispersion forces, which makes you want to think that London dispersion forces force molecules apart, causes them to disperse. But that's not actually what's happening. London dispersion forces are an attraction between nonpolar molecules due to temporary induced dipoles. Now, I know this is something that you learn in Gen Chem, but I want to review what this means. So if you have a nonpolar molecule, that nonpolar molecule still has one giant shared electron cloud amongst all the covalent bonds. But electrons don't stay in one place. They don't just live on a single atom. They're constantly moving around. And it is unreasonable to expect that all of the electrons are going to consistently be perfectly spread out. So at any given point, you might have a higher electron density in one part of an atom, even for a very small fraction of a second. And these temporary induced dipoles are actually enough to hold nonpolar molecules that shouldn't have any intermolecular forces together. These are also called induced dipole forces. The larger the molecule is, the greater the dispersion forces, because it's going to have a greater surface area. You also have to consider shape. Shapes that have smaller surface areas are going to have less London dispersion forces. Dispersion forces allow nonpolar hydrocarbons to exist as liquids and waxy solids. So for example, if you compare pentane and neopentane, they have the same formula. They're isomers of each other. They have the formula C5H12. The boiling point of pentane is 36.1 degrees Celsius, so it barely is a liquid. On a hot day, would not be a liquid. However, the boiling point of neopentane is 9.5 degrees Celsius, and that's because neopentane is actually going to have more of a spherical shape, and so it has less surface area compared to the more cylindrical pentane. So pentane molecules are able to get more tangled together, whereas the neopentane molecules are kind of like having a ball pit, right? The balls actually have a lot of empty space between each other. And that's going to be the same thing with neopentane molecules. So the boiling point's lower because there's less interaction between the molecules. So let's look at an overview of these intermolecular forces. If you have a nonpolar compound, the only type of force that they are going to experience are dispersion forces, and the strength of the dispersion forces is going to depend on the mass of the molecule and also the shape. Polar molecules have many more IMFs. You can have dipole-dipole interactions, and you're going to have dispersion. All molecules have dispersion forces. And this is going to depend on the polarity of the molecule. The more polar it is, the stronger those forces will be. Now, if the molecule is polar and also has HF bonds or HO bonds or HN bonds, you're going to see hydrogen bonding and dispersion, and also possibly dipole-dipole forces. You have a lot more options, and these forces are much stronger. And remember, you must have these very specific bonds in order to have hydrogen bonds. So let's look at how all of this affects solubility of organic compounds. Remember that the dissolution of a compound requires separating ions or molecules from each other. You have to be able to overcome the intermolecular forces that hold them together in order to dissolve something. And that is going to require energy, which is why sometimes heating up something can actually allow you to solubilize more of something else. The more or greater the IMFs a compound has, the less soluble it will be. And also remember the golden rule of solubility, that like dissolves like. So polar compounds dissolve in polar solvents. The solubility of a compound or the dissolution of a compound is going to require the formation of new and hopefully stronger or a greater number of interactions between the solute and the solvent molecules. So this is where the process of solvation and hydration come into play. So we saw earlier images of water solubilizing sodium chloride into sodium ions and chloride ions, and we saw those interactions between the sodium and the water molecules. Now, the attraction between the sodium plus ion and the chloride minus ion is actually pretty strong, and it's not necessarily true that the interactions between sodium plus and the oxygen of water is stronger, but notice how many interactions there were. I only drew 4 water molecules, but in actuality, there could actually be quite a few of those molecules around that sodium ion. So by creating more interactions, that is going to push the equilibrium towards solvation. So some terminology when you're discussing solubility. Solids and gases, we say that they are dissolved into liquids. When you mix 2 liquids together, we say that they are miscible. You cannot dissolve one liquid into another. So when you mix water and ethanol together, they will mix. It does look like one dissolves into the other, but we use the terminology miscible. So water and ethanol are miscible. They're not soluble, but miscible. And then we also have the term hydrophobic, which literally means water-fearing. This is a way of saying that something is incompatible with water. So for example, if you try to combine, say, vegetable oil and water, vegetable oil is highly nonpolar. It is a hydrocarbon largely, and so it's not going to want to interact with water. And so even if you take the two and you shake them up really well in a container, if you let it sit, they're going to separate back out again. So oil is very hydrophobic. It is very incompatible with water. And then we also have the term hydrophilic, which is water-loving, meaning that it is compatible with water. So for example, sugar. If you leave it out on a humid day, think of like cotton candy on a humid day. Cotton candy, when it's humid outside, is going to melt before our eyes. And what's actually happening is the sugar is so polar and so hydrophilic that it actually pulled in water and melted itself. Or it's not really melting, it just looks it. It's actually dissolving. So some guidelines for water solubility. And again, these are guidelines, not specifically rules, so there might be some things that fall just outside of these guidelines. Something must be hydrophilic or have a hydrophilic group in order to be soluble in water. Solubility is also going to depend on the number of carbons. 1 to 3 carbons is more likely to be soluble in water. 4 to 5 carbons are going to be borderline. It depends on the structure of the polar group and also how many polar groups you have. The more polar groups you have, the more likely it is that you'll be able to solubilize something. And 6 or more carbons are probably insoluble. But again, table sugar has 6 or more carbons and it's very water soluble, and that's because it's covered in hydroxyl groups. Large organic compounds greater than 6 carbons can be soluble when more than one polar group is present or if the compound is ionized. So for example, sugars, proteins, and DNA are all water soluble despite their size. And when we talk about acid-base interactions, we're going to specifically discuss ionizing a compound in order to make it soluble.